Okay, so good morning, everyone. The paper that I'm going to present, the title is Divide, Conquer, and Coalesce. This is a meta-parallel graph neural network for IoT intrusion detection at a scale. This is the paper overview. Basically, is on the domain of network intrusion detection systems for IoT networks. And here the challenge is the scaling graph neural networks to be used in detection for massive networks, basically, IoT. And the proposed solution, the authors, they designed this framework, Meta-Parallel Graph Neural Network, MPGNN. This is a framework that smartly, intelligently partitions, splits, divides, segments a large network into smaller groups. They call them coalitions. And this is for parallel processing. Now, the core philosophy here is that in the title, they say they divide, conquer, and coalesce. And basically, there is a large network in IoT, and they divide it in small groups. This is where divide enters. And they use the conquer because they are going to implement parallel network intrusion detection systems for each of the coalitions or for each of the groups to monitor the traffic here in each of the groups, trying to detect intrusions or suspicious activities. And at the end, these parallel coalitions, they are going to be ensembled into a prediction so they can issue a final detection. So I'm going to describe this in a minute. So basically, this is the context of the paper. What is network intrusion detection? Basically, it monitors network traffic for suspicious activities. And there are two approaches in the traditional base. So, I'm sorry, the traditional approach is based on rule-based. They basically have a database with all the attack signatures, and they are detecting any of these signatures to be flagged as an attack. And here the limitation is that the novel or unseen attacks, they are not detectable. This is what is better called a zero-day attack. And in the machine learning approach, basically the machine learning model learns the patterns from network flow data. And in that way, they can generalize and to detect previously unseen attack variants. And the data source here is NetFlow, which is network communication flows. These are records, basically, that contain endpoints that are featured as IP addresses and ports, and the statistical features, which are the packet counts and duration of the communication, and how many bytes there are transferred between the endpoints. So basically, the GNN, the graph neural networks for intrusion detection, the network traffic naturally forms graph structure. They have nodes, which are the endpoints, and the edges, which are the communication flows between the endpoints. And the features, as I said, there are packets, bytes, and duration of the communication. So the GNNs capture what traditional machine learning cannot capture. Basically, it's topological relationships between devices and communication patterns across the network. Also, a spatial correlation in attack behavior. The authors, they use a previously published model, which is the eGraph Sage. It's a state-of-the-art graph neural network based for network intrusion detection systems to perform edge classification, to label each flow as benign or unspecific attack. So basically, this model, eGraph Sage, builds node profiles from the surroundings flow patterns, and then uses those profiles plus flow features to classify each of the flow as malicious or benign. So for example, here we have a small example. These are the endpoints, A, B, C, D, E, and F. And the edges are the communication details between these edges. So for example, A is a workstation on a defined port, and B is the same workstation, but in another port, and so on. You can see node C, file server with this port, and D and E and F, they have, of course, their endpoints characteristics. And the edges, as they are described here, are F1, F2, F3, F4. They have different features for the communications. For example, F1, which is here, consists on 120 packets. This is the total bytes exchange and a duration of 30 minutes. And it's labeled as benign. But there is, for example, F3 that has an unusual number of packets exchanged between C and D, and it lasts very small time. So this is labeled as an attack, and so on. So this is the way that graph neural networks learn the patterns of the traffic. So basically, what does the graph neural network see? It sees that there are three edges connected to this node, C, F1, F2, F3, okay? Two edges have normal patterns, moderate packet long duration, and one edge has a suspicious pattern, 5,000 packets in 10 seconds, this one, basically. So this node is a hub receiving multiple connections. And for node C embedding, the meaning of this in the graph model, the model aggregates information from these three edges, and the model learns that this is a server endpoint that is receiving mixed traffic. So the key concept to learn from this paper is that they are using coalitions. It's basically they are grouping devices into these groups that they call coalitions. And yeah, it's a subset of IoT devices grouped together for localized intrusion detection. And in this paper context, the large network is partitioned into K coalitions. Each coalition has a coalition head, which is the network intrusion detection system, which is a high capability device that runs the local needs. And the coalition head collects network flow data only from devices within its location. And it reduces communication overhead because, of course, it segments the network into smaller groups of devices. The critical insight here is that coalitions can overlap, meaning that a device might belong to multiple coalitions. And this allows critical devices to be monitored by multiple intrusion detection systems. This creates some redundancy in the monitor. And this enables ensemble prediction for better accuracy. Now, what does meta mean here? So basically, there are going to be two layers of learning. In the traditional approach, the design fixed rules for partitioning networks. So the networks are going to be partitioned following some kind of rule, which is not adaptive. The meta-learning approach that the authors are proposing is basically learn how to partition the large network based on the data that they are monitoring. So the two levels of learning are basically, the first one is the base level learning, which basically is the trained intrusion detection models within each coalition, in each group. So each of the network intrusion systems is learning from the traffic that is going on through its devices. And the meta level, which is the core of the paper, it means that the model is going to learn how to divide the groups of devices, how to form coalitions so that the base level training works better, works well. Which devices should group together? So basically the meta here is how to train the reinforced learning model to learn how to divide the large network into smaller pieces for better intrusion detection system. So these the authors, they state the following question: why current graph neural networks based network intrusion detection systems failed at the scale? Because these systems that are based on GNN, on graph neural networks, they achieve a strong benchmarks performance. However, in the real IoT networks, they present deployment challenges. So basically, the graph data can reach gigabytes for large networks. Centralizing flow data creates massive communication overhead. Computational complexity exceeds IoT device capabilities, and the detection delays become unacceptable. And also, they state that there is a large number of devices by 2025. So these solutions are not feasible. They need some kind of scalable solution that maintains detection quality. So we have the large network of IoT devices, and of course, they're going to enter into the graph neural networks for learning the patterns of the traffic, and they go into a single centralized IDS. And this creates many sorts of bottlenecks. And the authors, they perform an experiment to establish the necessity of a better division of the groups of IoT devices. So the intuitive solution is to split the network, right? And into subgraphs. So therefore, it's like running parallel network intrusion detection systems. But the problem is that the random partitioning, this is very important, it causes severe information loss. Network traffic is really high unbalanced. The majority of the traffic is benign. And yeah, they have to take care in consideration that. Also, a random sampling excludes minority attacks types from collisions. And the result is that collisional network intrusion detection systems cannot learn patterns they never see. So for example, in this figure, we can see that, for example, here, there are 5 groups of IoT devices and an overall. Here is an experiment that they do using one centralized network intrusion system. Okay, so basically, you can see here the distribution of the attacks in the data. But when they divide it into different coalitions, into different groups, they can see that the patterns of the attacks are the distribution. It gets not the same as the overall. So here is some losing information. And basically this one is brought here. And you can see, for example, for this attack, there is no distribution of attack. So basically this group of devices, there is no man in the middle data that is going on there. So the network intrusion detection system in this group of devices is not going to be able to perform well for detecting this particular attack, neither this one, for example. So basically, this is the explanation of this graph. Dividing randomly the entire group of devices into different coalitions without having some intelligent way is going to create this problem that detection is going to perform bad because some of the coalitions is not going to be able to detect certain patterns of attacks. Now, random partitioning equals to severe detection degradation. That is the conclusion of that pre-experiment that they did. So in this graph, I'm going to go a little faster. In this graph, they are showing the performance F1 score related to the detection. So the same group of coalitions, the same group of devices, okay, they perform the F1. You can see a degradation. This is the centralized NIDS, centralized. And it achieves 0.83 F1 score. But the other coalitions, the other network intrusion detection systems for the other groups, they are performing very worse than the centralized one. And basically what I said, right? It's that the detection of this type of attack is very, very low. So basically this graph is about the detection of the attack types for specifically this coalition. Now, they propose this framework. This framework, MPGNN, basically is about learning how to partition a large group of devices, a large network of IoT devices. And it has two phases. So the first phase is the coalition formation. Basically here is about how to divide the network efficiently. It learns policy to partition network intelligently. So basically it's this block, the one on the top, which it has infrastructure for reinforcement learning. And this box, it learns how to partition the network efficiently, and then it implements it on the network. And then here, you can see the large IoT device group divided into several coalitions, right? And each of these coalitions is going to then be monitored by one network intrusion detection system. And of course, here is the graph neural network. But the paper centers on this design, how we can produce a better policy to devise the large network efficiently and intelligently, so the detection at the end, the detection of the attack is going to be highest as possible. And particularly, I'm going to describe now this box. The learning coalition formation policy is implemented in this sequence of blocks. So there is a Markov decision process. You can see here that there is the statistical features of the traffic and the topological information. And they combine it and they form what they call the attributed graph. So basically, these are the edges and the nodes with the traffic information. They enter it into what is called the actor network, and then it's going to go through the convolution layers. So in the first one node learns about the other nodes, the direct adjacent nodes. And in the second one, it learns into the second level, the second proximity adjacency of nodes. And then this state enters into what is called the critic network. So basically here, in the previous frame slide where it shows the implementation of these two levels, this block basically is the one that is going to be shaping, is going to produce, is going to be computing this policy, which is the one that divides the network. And that algorithm is the Stackelberg game. So basically, this is the implementation of this Stackelberg game framework. Now, the actor network is the one that initially is going to be issuing some policy to divide the network. And then this one is going to predict the error and try to minimize it. So basically, this is going to achieve the maximum reward, and this is going to minimize the error. And all this training is done with offline dataset. It's not online. And this is because the online approach is going to take a lot of time for convergence, and it achieves many challenges in the implementation. So yeah, basically this is the core of the paper's development. So there is the online reinforcement learning, they call it JATAC. This learns from historical data collected with arbitrary policies and avoids expensive online interaction with production networks, and uses graph convolution networks to capture topology. Then this part is the ensembling prediction, right? After the network is divided in the coalitions, of course, they're going to be to train the network intrusion detection systems on their own group, on their own coalition, and then they're going to take the average of prediction. It's a simple average, okay? So basically, this is the equation that they use. And each coalition selects the coalition head, which is the NIDS. And the coalition head collects flow data from member devices, constructs the local attributed graph, and runs the eGraph Sage model for edge classification. And the eGraph Sage aggregates all the edge features through neighborhood and then classifies each edge. And the ensemble prediction, it's the average, as you can see, from the different coalition groups. And this is the evaluation setup. Basically, they are using two data sets, which are the NetFlow version, because normally these data sets are tabular, right? They have one network event, feature 1, feature 2, and so on. But these versions are the ones that are suitable for graph neural networks. And they discover that, well, there are descriptions here about the data sets, 10 categories, 7 categories. This is the type, the number of endpoints or samples, okay? And basically the metrics that they are using to compare with other methods for the learning of the partitioning of the network are here. Now, in the results that they achieve is that for this data set, only 1.2% accuracy drop versus the centralized one. So remember that the comparison that they are using is all the network with one centralized network intrusion detection system versus their proposal, their framework. And yeah, they're here. Basically, this is the result that they achieve versus the centralized one. So there is a drop, a small drop. But in terms of training time, the reduction is almost 40% in training time. So this is faster to train, of course, because the division of the large network into smaller segments, smaller coalitions, it allows smaller groups of data to be processed and train the model. Also, there is a 3x scale reduction in the grouping of the nodes, 61 nodes per coalition versus 200 total. This is over here. And the F1 scores, it's 0.82 versus 0.42 versus random partitioning. So basically, with this result, they are stating that their proposal beats pretty much large, is pretty much better than partitioning the network in a random basis. Now, this is another representation on how well their model works. So basically, MPGNN collisions maintain balanced attack type distribution. So this is a random division of the network. There is also this algorithm which is using social network, graph neural networks, and the author's proposal. You can see here that all the attacks are contained in the different coalitions. So it means that each of the groups of devices, each of these coalitions, are going to be able to detect all of the attacks. But here, for example, using this algorithm for division of the groups of devices, the coalitions, you can see here, for example, this coalition, it doesn't have any attack. And the distribution of the attacks in the other two are different, are not equalized. And in a random division, they also have a very different distribution between each coalition. And also there are attacks that are not being monitored in one coalition from the other. It's hard to see because of the colors, but for example, this coalition, it has very low detection for this type of attack than the other ones, for example. And also there is a consistent detection across categories. There is a high F1 score for attack with strong spatial correlations. For example, for backdoor, here it's almost 1. And for denial of service, 0.93. For ransomware, 0.97, which are very difficult to detect attacks. There is a weaker on limited sample attacks. For example, man in the middle, 0.52, which is the average between this and this. Okay. Now, they also perform some experiments by removing different elements on this meta learning framework. For example, they call this experiment MPGNN MLP, which basically removes this block, and replaces with multi-layer perceptrons. So basically, this is the extension of that graph, that figure. They replace these blocks with multi-layer perceptrons. Of course, this learning model is not more implemented. And the drop on the F1 scores goes from 0.82 to 0.77. And the conclusion from here is that it is necessary some model like GNN, graph neural networks, to understand the topological patterns of the traffic. Multi-layer perceptrons that do not learn topological patterns. This is tabular, basically tabular learning. And the other experiment is unweighted adjacency. And basically, unweighted adjacency, it means that they are not going to consider topological information here. They replace it with 0 or 1, and they only rely on the tabular information. And the F1 score drops to 0.43. Finally, the third experiment that they do is the implementation of DQRA. This is removing a stabilization mechanism. So basically, what it means is that these two blocks, the Bellman consistency and the logs of critic, is going to be removed. So this relative pessimistic loss is going to enter directly into this critic network. And here there is a slight decrease in the F1 score. So it's around here, this value versus this value. So with all that, they managed to prove that their proposal is performing better than the other solutions, which the other solutions are less complex, but they decrease the performance, of course. So finally, the limitations and open questions they leave in the paper is that generating the training data requires running arbitrary network intrusion detection system first. Also, they assume known attack types. The reward penalizes missing categories, problematic for zero-day detection. New attacks are not going to be able to perform well in the detection. The scale gap also, they establish that there is a limitation because they test this framework with around 300,000 endpoints, which is 300,000 different pairs of IP addresses and ports. And in real scenarios of IoT networks, it can be 100 times larger. Also, the temporal dynamics, our scale coalition updates might be too slow for rapid attacks. Yes, I mean, they are stating that if there is an update every hour of the division of the large network into coalitions, that convergence might be too slow for attacks that are very fast in time. Yeah. And then finally, baseline fairness, federated learning. There is a comparison that they use random partitioning. So basically, they are not comparing the same kind of algorithms for the division of the network. So in summary, the core insight is how the network is partitioned that matters more than whether it is parallelized or not. And the technical contribution of this paper is that offline reinforcement learning framework learns coalition formation as meta-knowledge. And the practical wins that there is a reduction of 40% in training time, and is very close to a centralized approach when they use a centralized network intrusion detection system. Also, it is deployable on resource-constrained infrastructure. And the open challenges that they state is that zero-day attacks, which are new attacks that the network hasn't seen, the network intrusion detection system has not seen, they are very difficult still to be detected. And there are problems also in large escalations, and the temporal adaptation still remain to be a challenge. So yes, basically this is the summary of the paper. I'm ready to take your questions.
Thanks for the presentation. 질문 있으면 질문 하시죠. I have a couple of questions.
Yes, Professor.
In the process of graph modeling, I feel that even for the same edge between nodes, for example, from in the slide of page number 4,
Yeah.
here we have flow F1 from A to C. Here it is labeled as benign. However, I feel that there are other edges as well, like malicious or multiple benigns. Is it possible in this scenario? Is it covering those scenarios here?
You say if this is the same features here can correspond to an attack?
Actually, in each edge, it
Yes.
assumes in this figure only one label.
Yes.
However, actually, there could be multiple labels for the same edge. Is it possible in this scenario?
Yeah, I mean, given the data set that they are using, is not possible because they are not classifying the data into only into a type of attack. Is
But in
there?
reality, it could be possible, right?
Yes, yes. In reality, yes,
But
it can be at
it does
more.
not consider,
Yes,
this paper does not consider about that. Okay.
yes. This paper is only taking into account the type of the tactic, let's say, right? Like denial of service of brute force, but specific techniques for each of these attacks are not considered. Yes,
Okay.
maybe they are using. It's because of those data sets they are using. These ones, these two, they are fixed. I mean, yeah, they are fixed attacks. I mean, they are using one technique of an attack, for example, for brute force or man in the middle. They are not using a variant of different techniques for each of these attacks. Yes. Therefore,
If there are if there are multiple different flows between two nodes, then how do they label the the actual flow for the edge in the data set?
okay. So these data sets already have the information, but basically it's because they are using this source IP and destination IP. And if they match, for example, 10, 1, 1, and here if they are fixed across the communication of the dataset, they are labeling as, for example, in a specific port, let's say 443, and here random. So this is going to be some kind of SQL injection, right? Because it's attacking a website. Okay. So basically,
But some of them could be just benign network
yes,
traffic. But how they uh, clarify them?
yeah, I was about to say that in the formulation, in the manufacturing of these data sets, they have time windows. So from a specific time stamp to another, that all those samples that they have these IP addresses and this
Mm,
port, they are assigned SQL injection.
okay, I
It's
see.
not like the one that we are doing, for example. We are
Mm,
doing at the level of host process. We are
mm,
being more granular.
okay.
Mhm.
Uh, and the regarding the definition of collision, collision here means the concept of a semantic unit for the graph, not the physical unit, right?
Uh, yes. Basically, is how to divide the network in smaller groups,
Mm-hmm.
but a device can be in different groups. So this
Okay.
is not physical. Yes,
Mm.
it's only semantic.
Uh, okay, then they divide the entire graph into multiple collisions, right?
Yes, here, for example,
Mm-hmm. And then they apply the GNN for each collision.
yes, here, each
Yeah,
of these
I
blocks.
wonder that how do they consider the relationships between collisions? I think they are missing completely.
I haven't explored that much deeper in the paper, Professor, but here it's
Mm-hmm.
supposed this block is supposed to compute the better policy for that division. So I think uh, it doesn't precise how is it doing in terms of reward. I mean, if they are monitoring the F1 score of these coalition groups,
Mm-hmm.
I don't know if they are doing that.
Mm.
Remains an
But
uncertainty.
the information the between collisions are missing during the calculation, right?
Yes.
Only independently working for each collision.
Yes, exactly. They are
So in that
independent.
case, they do not need to maintain the entire graph. It doesn't make sense.
Yeah.
That's a critical limitation for this paper, I think.
Yes.
Anyway, uh, I think the core part is to build a collision from the entire graph. But I wonder what's the final outputs for the process of collision formation. I expect that they they should generate a group of collisions. However, from the page 11, I think that shows the entire process for the collision formation. However, I do not clearly check which parts are uh, describing about the output of the process.
So what I understood from the paper is that, of course, this block, the actor, is the one that delivers the first policy, and then um, it computes from the graphs, from the samples, the graph samples. It computes if the detection of different attack patterns and also the distribution of the attack patterns the attack traffic that is going on that coalition, it's evenly, right? And also if the F1 score is high. And with that information, I think they feedback this critic network. And of course, the prediction it's minimized, and it goes until convergence. And that's why they managed to output this graph. For example, their framework, each of the coalitions with this framework, with this figure, they are stating that each of the coalition is able to detect these attacks, these different attacks, and the distribution is somehow even, right, between the attacks. For
Okay, I see.
example,
But my question is that I believe that the final process for the collision formation should be generating the partitioned graph collisions. However, I can't find the exact part for that in the figure.
mm,
Anyway, by
mhm,
the process, they will uh, generate the partition, number of partitions, right?
yes,
Okay.
yes, they generate how many device is for one
Hmm.
coalition and how many coalitions are going to exist.
Then the core idea to make a partition here is make the balance between collision.
Yes,
Is that
exactly.
all?
And to also to basically they are looking forward to how to segment the network more intelligently. Basically, is to divide a large network into subgroups so they can implement a network intrusion detection system for each
Hmm.
group that is able to detect all the attacks
Mm,
that occur in different coalitions.
okay.
Mhm.
And another one is the in the experiments, there's a global method. What does it mean? Global means the just the consider the entire graph to work with GNN.
Yes, this global is the entire IoT network with
Mm.
one centralized network intrusion detection system.
Uh,
So here,
then they are only focusing on the graph-based approach. They do not compare with the other approaches without graph, right?
yes.
But why should graph be required in this problem? Even without the graph, this problem can be solved.
Yeah.
Sometimes it could be
Okay, okay. But
much more effective than using graph.
no, I'm sorry. But this global, this
Mhm.
NIDS is based on GNN.
Yeah, that is also based on the graph.
Yes. So basically, the partitions is not better, slightly
Mm.
not better, right? Because the centralized NIDS approach is this number, which is slightly higher than their framework,
Mm.
which is
But
quali.
the my question, the my primary concerns about the I wonder why graph should be required for this problem. Any
Okay.
justification for that? Because the graph adaptation is the proposed idea by this paper, but other approaches completely possible without graph.
Yes. Yes, they are. Maybe it's because the research that they present in the related work maybe is that they are achieving with GNN a higher detection pattern, which is based on graph neural networks. And they are not uh, testing with another approaches. But here in this experiment, when they eliminate these blocks and replace them with multi-layer perceptrons, which is not described that much well how it is, but they are the ablation studies is about removing elements of the proposal, right? So basically, these two blocks are being replaced with multi-layer perceptron, and this one is not able to learn from graphs, basically. So the F1 score drops according to them.
Mm-hmm.
So from that experiment, they state, okay, if we do not use GNN, then the model is not able to learn graph patterns. So the consequence of that is that the F1 score drops. That's the statement that they do. I don't know if they are using another, no, I mean, I know that from the paper that they are only using MLP, but they are not using tabular data, right? Like eliminating this and only leaving this and putting into some LSTM or transformer here, right? They are not doing that. They are stating that we are going to use graph approach for topological features. And that is because that model E graph Sage, it has achieved the top, I think it was around 80% of accuracy detection. So this model, they are not, they're reusing it from another paper. But of course, their proposal is the design of this reinforcement learning design. So it can design a better division of the network. But they are not using another approach that is not GNN, only here, and it drops. And that's a
Okay.
conclusion that they have.
Okay, thanks.
Mhm.
다른 질문 있어요? 한글로 해도 돼요. 한글로 해도 오스카 이해할 수 있어요. 질문 없어요? 그 임보영 학생은 여기 지금 아까 사용했던 지금 여기서 지금 파티션 만드는 방법을 그 우리 KDD 제출했던 논문에서 그러니까 컨티뉴어 러닝 그래프 거기서 임밸런스를 좀 해결하려고 시도를 했던 메커니즘들이 있었잖아요.
네,
그때 이제 이런 거 좀 참고해봐도 좋을 것 같네요. 그거 계산할 때.
네, 알겠습니다.
그거 정도가 여기서 우리가 얻어낼 것 같네요. 다른 질문 없으면 다들 점심 맛있게 먹고. 네, 수고하셨습니다. Thanks for your presentation answers, Oscar.